Swayam Prabha. Digital India. Educated India.
So today we are going to start with simple stuff, some simple notation, some basic examples. So I will for the most of the initial lectures that I am going to give before the midterm, I am going to largely follow it from the book. The first book I gave as a reference last time, that is Introduction to Probability Models, and by Random Process for Engineers. Okay, fine. So as this we say, this course is about Introduction to Stochastic Models. The book, the first reference I said, that says Introduction to Probability Models, right? So what's the difference? Probability and stochastic, they are the same. So what we are interested here is, so okay, the book says Introduction to Probability Theory, and our course is titled as Introduction to Stochastic Models. Theory is used to analyze models, right, develop models. So what is this probability theory we are going to develop to study models, right? Many things we are going to face in real life, they need not be certain, right? There is always randomness associated with them. So is there a way like I systematically model them? First thing is I need to model them. If I can systematically model and then I can analyze, and then whatever the analysis I have done, I can tell that analysis to somebody else, and that guy will understand it. If you can talk to him what is the model that you took it. So fine, there will be, like if you give me a realistic scenario, like nobody is God, right? Like you can't perfectly model it. So you are going to model it according to some set rules, which we are going to study in this rule. So if you are going to do that, then it is possible for you to explain the model you have developed and what all the analysis you did, and then that guy may not or may agree with your analysis depending on whether he agrees with your model or not. So broadly, we start analyzing or we start to study some basic terminology that will be useful for us to start talking a stochastic model. That means, yes, I am trying to model a system, there is uncertainty, but I want to still model it. And what is that notion of this stochasticity? We are going to make precise by going through sequence of terminologies now. Okay, so the first thing we are going to study is so I am going to call anything. So when you are going to model something, yes, there are a set of possible outcomes possible with that. I am going to denote the collection of set of all those possible outcomes as sample space, and I am going to denote it by S. So whenever now I call experiment, it is implied that I mean an random experiment. That is, the outcome itself you can't a priori know what is that it is going to take. So okay, let's now try to distinguish what is a random experiment and what is a deterministic experiment. Can you tell me a certain thing in life which you are sure shot to know what is the outcome is going to be? Determining shape of earth. Okay, let's say, I mean, God has built something, I mean, that nobody can change. These are things, certain things are fixed, right? So for example, laws of physics, they are fixed, right? Like, you know, that is how it has to behave. These are fundamental laws, you can't change. But now let's say you have a toss of a coin. Can I consider this as a random experiment? So the outcome could be head or tail, right? And each of head and tail can happen. I mean, I don't know, like when the head, I can't a priori when you toss a coin, I don't know whether it's already going to be head or coming to or head or tail, and that's why. So fine, that is possibly the reason where the coin toss used to decide who is going to bat first, or which court you are going to choose, or who is going to serve first, because that is possibly a very random event, and maybe it is not going to bias towards anybody. We will talk about this, what I mean by bias, but at least a priori we are not going to be saying, okay, this guy is going to be favored, this guy is going to get whatever he prefers. So we are going to do that randomly. So we are going to denote sample space by omega, and depending on what is that random experiment we are talking about, this could be a different set. For example, if I am going to talk about coin toss, what is this set is going to be? Two outcomes, right? Just it is going to be head or tail. Right now, let not put them in flower bracket, just let me write this head and tail. Other, you might have already talked about it 1,000 times, like toss of a dice, right? When you are going to throw a dice, what are the possible outcomes? 1 to 6, that is going to be our sample space. So this is this is a random experiment, because if I throw it a priori, maybe I don't know what is the outcome that I'm going to see out of this. So let's say that's, so when I asked you, can you give me an experiments where the outcome is almost deterministic, it is deterministic, you have to think, right, like something immediately does not come to mind. If I ask you, okay, give me an random experiments, I mean, everything that comes to mind is possibly random, right? Possibly, like, there will be a class today, hey, it's random. I don't know what happens if that lecture gets out, you may not come for class, or you may for some reason may not attend the class, for whatever various reason that is not under your control. So many things are random in life, and if you want to model them or analyze them, so we need to have a systematic, we have to develop it systematically. So one concept, we are going to use this notion of sample space. So instead of one coin, suppose I am going to take two coins and throw them. I mean, in each trial I am going to toss two coins. What could be possible outcomes for me? So I can see possibly head on both sides, on both coins. I am going to see tail, or first is head, other tail, or and similarly, if I am going to throw dice, what is the possible outcome? 36, right? Maybe the better way to represent that is through a matrix where it is So these are very toy trivial examples where as soon as I tell what is the experiment, you right away know what is the outcome is going to look like. Okay. So we will leave up to our convenience how we are going to represent it. When it is as simple as I didn't tell you, write it like this. When it is more convenient for us to write it in matrix form, we will write it. It is just like collect. So each one is an outcome here. So we are going to say each element in this omega is an outcome. We are going to say so this, as I said, are simple things. It is pretty easy to write down, but often, I mean, you are not going to model what coin toss, right? Like you are learning this course to do much more complicated things. For example, you want to model how the weather prediction, you want to model my trajectory of a missile, or like my trajectory of a satellite, whatever the things, or whatever, like if I send a signal, whether my signal will reach my destination, or if I am going to take a particular route, whether I am going to reach my destination within a stipulated time. Many things you want to model. So in that case, we always not worry what is the, we are not always in sit down and first write, okay, what is the set of possible outcomes in this. So for example, if I am interested in, let's say, find average height of all Indians, so then what could be sample space in this? Yes, it is random. I am asking about what are the possible outcomes. Yeah, any value, right? Like maybe the shortest person is, let's say, from 2 feet. I don't know if it is I mean, I'm saying about adults. Let's say some average age of Indians who are 21 plus, and maybe like something like maybe 7 or 8 feet. All numbers in these things are possible. So you are not going to just like maybe write down exhaustively individual value, but maybe write a range. Or let's say you are trying to model weather forecasting. There, I mean, millions of parameters will be involved in how the things evolve, and based on what is the value of this millions variable, different possible outcomes are there. We just don't try to enumerate them, but it will be on the back of our mind, like what is the possible outcome is. Okay, so whenever it's possible, we just enumerate them, but whenever, say, sometimes I may just say, okay, this is a sample space, but that sample space may be like abstract. We may have its visualization, but we may not write it formally on a paper or on a board. Okay. Now comes event. So once we are given a sample space, then we talk about events. What is the event? For example, in your coin toss problem, what are the possible events? The possible event in a single toss of a coin, either it's head or tail. And when it is a toss of two coins, the event could be like both showing up head, both showing up tails, or one of them showing up head, tail, and otherwise. Okay. And we are just simply going to denote an event by like this, and then you will be always interested in the questions like, okay, what is, if I want to do a 2 coin toss, what is the likelihood or probability that you are going to see some value that the outcome is going to, the event is going to take one of these possible values. So let us say E and F are 2 events. Then we say E and F are mutually disjoint What is this? It's a null set. What does null set means? It does not have any element. Okay, so we are saying what does the interpretation of E intersection F equals to null set means? So they don't have any common element. So when they don't have any common element, we exactly call these 2 events are mutually disjoint. Or for sets we call it mutually disjoint, but these are events, we are going to call them as mutually exclusive. So similarly, let us say we are going to have E1, E2, like En, like let us say these are collection of events, they are all coming from the same sample space. We can talk about their unions, we can talk about their intersections, and we can take about any combinatorial structure, that is the union of some along with intersection with others and all. For example, if you want to, let us say I want to take union. So here let me say I equals to n. So what is this? So I am just taking union of all the sets. Now suppose let us say E1 is HH and E2 is HT. What is the union of E1 and E2? So union of H1 and H2 says what? The first outcome is head. That's right, like you don't care about second. Second can be either head or tail, but you want the first outcome to be head. So in that case, okay, these E1, E2 could be some events in your space, but you can combine them to derive more events. Okay, and similarly, you can look at intersections. So I could write it as the intersection of. So what does intersection of set of events give you? The common element. So in the same example, this HH and HT, the intersection will be what? So, okay, so notice that when I said E is a subset of omega, right? One element can also be a subset, right? So here these are the individual elements in the set omega. For example, E1 could be this element and this element, and E1 could be or E2 could be these 3 elements. Okay. So now when you are going to take intersection of, let's say, just 2 elements, in this there is nothing common between them, right? But suppose you are going to define E1 to be this set and E2 to be this set, you can do that, right? Like you can take this because both are subsets of my omega. What is that intersection is going to give you? It requires that both tossers give me tails. Okay, now we will get to the notion of probability, okay, and probability of events. So we will make the notion of probability precise more, but let's try to write down informally what we mean by probability of events, okay. So you take an so henceforth when I say an experiment, a random experiment, that will always come with an associated sample space. So when I say random, it's going to take all possible some possible outcomes. I'm going to call that a sample space, and now on that space I have an associated event space, and I'm going to say this probability is something that is going to assign a numbers to this event such that
So in first point, does it need to be proper subsets?
here not necessarily, it could be full event space. So I mean when I use the notation subset, not necessarily it a strict subset, it could be entire set itself, okay. I mean I may, if I want to specifically say that it's a proper subset, then I'm going to use this notation. That means equality is not included, okay. Otherwise if I just write it, it will be just like this. Yeah, it says that this function P is basically a function, right? It tells what is the value assigned to each possible event in omega. It says that for every event we will take a value which is between 0 1, and the entire sample space it is going to give a value of 1, and if you are going to take a sequence of mutually exclusive event, the probability of their union is nothing but sum of their probability. So all of you understand what I mean by a sequence? So you all might have heard about sequence of numbers, right? Sequence of real numbers like x1, x2, where x1 is a real number. For example, xn can be, let's say, 1 by n. So what is xn converges to? If I set xn equals to 1 by n, but now I am talking about sequence of events, right? What do I mean by sequence of events? It is just like indexing, like I have set. So what I mean by sequence means I have an indexed set of values, right? Like you give me any integer, natural number, that index is associated with some number. So if I tell me I, xi is the corresponding number. If you tell me n, xn is the corresponding. The same notion we are going to use for the sets, like this. For every possible index, there is an associated set. If you have such thing, if you have such a sequence of this, it is going to be just this. Okay. Now and we are going to refer to P of E. For any P of E, we are going to just say is the probability of event P. Okay, now let's see some of the things associated with this probability. And let's say we can come up with some such probability function. Suppose let's go back to our basic coin tossing problem. So we have omega, which consists of heads and tail. Event can be either head or tail. So let's say for if I say it's a fair coin, what is that P of h you want to assign? 1 by 2, right? Like both are equally likely. If let's say it's a biased coin, then let's say somebody has tweaked the coin and probably likelihood of h is more than tail, then maybe you want to assign probability of head to be something greater than 0.5. And now if I go to dice problem, what is, if I say it's a fair die, what is the probability you are going to assign to any number? Just 1 by 6, all of them are equally likely. And if again, but that is not the necessary, right? If you feel that you design such thing such that it could be biased, so you may, if you make some face heavy so that it comes more likely, if the design is like that, you are going to assign more than 1 by 6 for that. And also note that this probability requires that P of S is equals to 1. That is, it is all possibilities, right? You are going to say, okay, I am doing this event and these are the possible outcomes. When you do this experiment, one of the things that has to happen, right? Otherwise your definition of outcomes sample space was incorrect. Okay, fine. You can, it's up to you, like you can define based on your model how you want to decide this P. So you would like if you want to model a fair coin, you would like this P to be half for both the events. And the same thing, if you want to model a fair dice, you want to set P of I to be 1 by 6 for all I 1 to 6. But that's not necessary, right? This is up to you. This is your function that you want to use it as whenever you want to model. Okay, fine. Suppose let's say I say a fair coin, and you keep tossing it, keep on tossing it, and after large number of toss, you count how many heads you got and how many tails you got, and divide it by number of tosses you made. What do you expect that to be? So if it's a fair coin, you expect that to be close to 0.5, right? So in a way, you want to kind of interpret this probability as frequency of occurrence of that event when you do this experiment again and again. Okay? So let's try to, we will get back to this again. Okay, fine. Now, suppose let's say E and F are two events. And I am interested in finding probability of E plus probability of F. Okay. I am not saying that this E and F are disjoint. Okay, they could have some common elements. If that's the case, what is the sum you are going to be like? So one natural way to do this is either take probability, so take it like probability of UF. You want to do correction for this, and that is going to be, and why is this correction here? They are not mutually exclusive, right? Like suppose if you have a set A and another set B, this set is entire this and this is B. If you are going to take this entire set once and you take this entire set once, you would have added this region twice.
We should add it, I think.
Yeah?
We should add it instead of subtracting. Because you need to find PE plus PR. E plus.
Instead of minusing, there should be a positive.
Oh, right. Okay. So, right. So, I mean, just by this Venn diagram geometric interpretation, you will see that fine, when I did this, I counted the common part once, so I need to do it again because that has actually been added twice on the left hand side. Again, this relation is fine, it makes intuitive sense, right? The probability should be such that it should satisfy these conditions. So now we have introduced this basic notion of what is sample space, what is event, and we have introduced this notion of this probability, and we want this probability should be such that it satisfies some intuitive properties. Okay, fine. Instead of going, okay, I want this property to satisfy something, what we will now try to do is start with some basic assumptions on my probability space or my event space and define probability in a systematic way so that whatever the kind of things we want, they actually naturally follow by our basic definition. Instead of, okay, we want this to happen, you start with your basic framework such that they are induced to happen. Okay.